Hello everyone and welcome to another of our webinars from SFP EQ student chapter. Today we are featuring Nate Lobel. So thank you, Nate, for joining us. He's a chartered fire safety engineering with degrees in chemical engineering and fire protection engineering. He has broad experience in in a range of different sectors in Australia. He has been linked with with the infrastructure boom that allowed him to get various stages in different projects as the Melbourne Metro, Cross River Rail, Brisbane Metro, among others. So he's also been involved in different industry initiatives with the focus on the future of the fire safety industry. For example, he has collaborated with our research group on what's the future for the fire safety engineering professionals. I hope I've made a decent introduction for you, Nate. Thank you for joining us.
Thank you for having me.
Yeah. So the floor is all yours for you to speak. Yeah.
All right.
I'll stop sharing my screen so you can share yours.
Perfect. There we go. Can everybody see that?
Yeah, that's perfect.
Great. My understanding is the way this is run is if you have questions, please just put them in the chat, and at the end we'll hopefully have time to get through as many as we can. Thank you for that introduction. So as Julie introduced me, I'm Nate Lobel. I'll be giving sort of a very high-level chat on infrastructure fire life safety design. Quick things of what I will and won't cover today. So it's going to be a little bit of knowledge on a large range of topics. I'm not going to go in depth on any of them. I'll talk a bit about why tunnels are so different from buildings and typical or common approaches to tunnel fire safety design, or fire life safety is typically how we refer to it in infrastructure. Noting that, like buildings, every underground project is a bit different and unique. Some things I'm not covering, because these inevitably will come up in questions, are some existing assets and risk-based approaches for those, specific system design or modeling calculations. I won't go too much into stations, though I'll touch on them a bit. The procurement process for infrastructure projects tends to be very different from buildings, but again, we'll go into that. Crossovers and intersections are specific, I guess you could almost call them hazards within an infrastructure alignment when we're talking about underground. It's where two separate rail tunnels might merge, that trains can cross from track to track, or a road tunnel with exits and entrances, which require extra analysis. Rolling stock, which is a term used in infrastructure to really just describe effectively the trains on a rail line. That in and of itself effectively is a whole presentation, a whole discipline almost, in how they're assessed and how they're designed and how you do fire testing and calculations. I will touch on risk-based approaches in terms of the frameworks we use in infrastructure, but I'm not going to go into detail in QRAs or bow ties. And today's focus is very much rail and road tunnels, more so rail, but it should acknowledge that there are other types of tunnels that we design and work on, hydroelectric power stations. So for instance, Snowy will have a giant access tunnels down to a cavern. Airport baggage conveyors can sometimes be underground between terminals and will be treated like a tunnel as well. Also, when we're talking about infrastructure in fire safety engineering, we're typically talking about road and rail, and particularly today will be about the tunnels and underground. But it's just worth pointing out that infrastructure as a whole is much more diverse than that. Aviation, energy, water, health, emergency services are all essential infrastructure in the built environment, and all require special considerations. In terms of some reasons that infrastructure design is so different from buildings, when we work on a building, we're very much dealing with normally one client who sometimes they're using the building, sometimes they're just building it to sell. And while we say buildings are for people, really they're for a smaller subset. when we talk about infrastructure, and particularly transport infrastructure, there's a huge public reliance on it, whether it's passenger rail or freight, or a passenger road or a freight line. This public reliance creates this social expectation of safety. We all expect that the things we touch every day that are provided to us through our taxes and the government are safe and available. And they also bring a huge economic benefit to a region. Globally, almost every metro line in the world loses money on the fares, but some of them make money in other ways, or more often it's just realized that for every dollar you invest in infrastructure, you may lose money day to day, but the overall economic benefit is much, much greater. They're required to operate 24/7, 365. And as an example of that, on the right, I won't try to pronounce it, but this is a tunnel facility in Switzerland that I got to go to on a trip with Siemens a few years ago. And it's quite an interesting place because what they do is they rent out different segments of this underground tunneling system to companies who want to test new methods, want to do material testing, or want to teach people how to install something. During our trip, we spoke to one such person who was using the tunnel to teach their team of contractors on how to line a tunnel, because they had been awarded a 30-year contract to line an existing metro system in a city in Europe, where the existing system is just bare rock walls in the tunnel, and they need to line it to increase the lifespan of the system, but they refuse to shut down the system for any period of time. So every day for the next 30 years, the contractor has 6 hours to decommission all the services, remove the rail line, drill out more of the tunnel, add in lining, recommission and reinstall the services. So they were renting a tunnel in this facility to test that. And that sort of process of 6 hours every day for 30 years, because of how critical it is that they don't shut down the metro system in that city. These systems are really critical to day. They bring in food, medicine, raw materials, finished goods, and not having certain roads or certain rail lines can have a really big impact on the city. Infrastructure is also quite different from buildings in that often it feels like it's its own language. There's lots of acronyms and lots of terms used in it, and they can be a bit confusing because many of them are historical. As a little indication, on this figure, you see some things called the 4 foot, the 10 foot, and 6 foot. None of those are necessarily 4 foot wide or 10 feet wide. It's just the historical names because at one point they were in some other project, probably back in the UK. But there's a lot of those terms in infrastructure that you will learn through a project or through a process. On infrastructure, we also deal with very different design inputs and different clients. So most of the clients in the built environment don't know much about building a building. They might be in a whole different industry. They just want an office for their workers, or they might be selling goods or operating a restaurant. They know how to do that, but they don't know much about buildings. In infrastructure, we generally get the ability to work with operators, and whether you're working with the actual organization that will operate the rail line, or some projects they have what's called a shadow operator, somebody who represents them and brings in that insight. And in this way, your clients have a lot more skin in the game. They're working to design an asset that they will need, and that typically will have a design life of 100 years, if not more, versus buildings, which are much less. Similarly, the building code of Australia isn't really applicable to tunnels. It is applied in spirit to stations, but it's still not greatly useful in stations either. Australia does have a performance-based standard for tunnels, but it is very much high-level guidance rather than how to design a tunnel. Keys as well is that infrastructure is very much a risk-based approach. It's important for us when we're designing infrastructure to understand likelihoods and consequences of items. And in that respect, we'll look at things beyond just simple safety. We'll look at operational continuity and repairability, because as we said earlier, the infrastructure is so critical to a building. We can rely on international standards. There are NFPA codes for rail and for road tunnels. If you're working on a project, you'll also typically be given what's called a PS, a PSCR, an SWTC, or some other acronym, their performance specification or a statement of works and technical criteria. This is you could almost call it your building code for the project. It's the requirements for the project that you must achieve, and they're typically quite specific to that project. But often, particularly for fire, they're worded as this is the minimum. So it might list 15 fire scenarios you need to consider, and it will clearly say you have to also prove that there aren't other ones that are relevant. And this last one here, Rail National Safety Law, or RNSL, is operated by the Office of the National Rail Safety Regulator. Obviously, this applies to rail, not road. This was a nationalized law in, I think, 2013 or 2014 that sets out a risk framework for how rail operators operate, and it extends to designers and maintainers and even to decommissioning rail systems. It creates an obligation to reduce risk to safety so far as is reasonably practical, or SFAIRP, which I'll talk about a bit more. And it views the idea of demonstrating safety, safety assurance, as an actual process, not just saying, I have a safe design, but actually showing the process you've gone through and showing where you do have risk and understanding those risks. Because there's no way to eliminate all risk, which is another reason why when we design these, the operators are involved, because the resulting risk profile is something that whoever is operating the rail system, let's say City Metro, has to acknowledge, be aware of, and be willing to accept. If they can't accept it, then the rail system, they can't operate. In that respect, for infrastructure, we look at obviously maximizing occupant life safety and allowing for brigade intervention, both of which are typically covered under the building code. But we also look at that operational continuity, excuse me, and reasonably protecting from damage, total losses, and looking at downtime, repairability. Now, earlier I mentioned SFAIRP, which you see in the top left. SFAIRP is a risk reduction framework, is how I would phrase it. It's a mindset that you can use to reduce risk. Another one is ALOP on the top right there, stands for as low as is reasonably practical. I'm going to briefly touch on these. In Australia, on rail projects, the Office of the National Rail Safety Regulator has very clear guidance saying that these are the same for Australia. Under their purview, they mean the same thing, you continue to use them. I'm going to explain a bit more about how they're viewed internationally, because, well, frankly, nowadays we have the internet, so if you are searching for guidance on it, you might find something for ALOP, and in other countries, quite often ALOP and SFAIRP are viewed differently. So if we look at the risk process a bit, ALOP and SFAIRP are both similar, that if a risk is not tolerable, it's a very high consequence, very high likelihood, it can't be accepted unless there's something very extraordinary going on. As the likelihood and consequence is reduced, there's this region called the tolerable region, where you look at a risk, it's something that you could operate with, but you probably still want to reduce it. I would say that those two sections are typically the same under these two frameworks. It's this last section where things differ. So under as low as is reasonably practical, well, ALOP, there's this idea that a risk that lies in this region where it has a very low likelihood and very low consequence is just broadly acceptable. You don't really need to do much more assessment on it. You would record it for tracking and to make sure that the risk never increases. Duty of care might require you to do more, but if we're just looking at ALOP effectively, the process can stop. Whereas if we're talking about SFAIRP on rail design, you have to continue to prove that further risk reduction is impractical. Just to show you an example, I will go through the process of this. So this is risk land use planning criteria from New South Wales, HIPAP papers. These are essentially those three regions. Down here is broadly acceptable. This is the tolerable region, or ALOP region is called, and this is intolerable. You'll note just a couple lines in there in terms of fatalities, risk frequency. if we look at that process, as an example, we have a risk identified in the tolerable region. We go through each process and we implement a reduction measure that reduces the risk to broadly acceptable. For ALOP, the process is over, but we still need to monitor the risk. Under SFAIRP, the idea is that we still need to identify further means of reducing or eliminating the risk. It means that cost benefit can be considered, but only after you identify the potential options for minimizing the risk. And that's really important because that brings transparency to the process in terms of, here are a bunch of things we did think about and consider, and then we looked at the price tag and it's quite easy to tell it's ridiculous. SFAIRP can only end when the cost benefit is grossly disproportionate. So effectively, you can almost think of it as ALOP as an acceptance criteria, and SFAIRP, the acceptance criteria is a cost benefit analysis. Another area where infrastructure is a bit different is in terms of how we think about fire scenarios and how we analyze them and talk about them. Typically, we talk about design, high challenge, and extreme scenarios rather than, say, a base case and sensitivity. We also are a lot more explicit in this field in terms of the risk. So I went through that SFAIRP process. That SFAIRP process is not so much a mindset, it's a recorded on paper in a report process. In infrastructure, it's really clear that we are transparent and open about we have risks and we acknowledge them. For these sort of scenarios, it's not unheard of for a high challenge fire to not always have a deterministic safety factor of 1. So your model might show that some people are injured or some fatalities occur, but then you can look at the risk-based approach. Extreme scenarios are things that in a building we would just look at it and be like, that's not going to happen. It's not very important, or it's way outside of the building code's purview. In infrastructure, most of the time you're not expected to design for it, but you are expected to be able to understand and communicate what are the consequences of it for acceptance. Because if there is an extreme scenario that has some catastrophic consequence across a whole region, maybe they might want to look at that impact and say, no, we should do a bit more design of that. So often they're assessed to inform understanding of the risk, but again, on a frequency basis. And the other big difference is in infrastructure, it's fairly common for us to actually look at a damage model in terms of exposures, injuries, and fatalities, rather than just a pass-fail tenability. Now I'm going to move a bit more back into tunnels themselves and typical construction methods. So in working on tunnels, it can be quite helpful to understand how they're built and how systems can actually be brought into them, because it gives a better appreciation for how difficult it can be to add a system or make changes or maintain a tunnel. So this slide sort of shows 2 of the different methods of tunnel construction. So on this top right here, we have a road header. So this shaft would have been dug, and then this machine would have effectively been put down here, and it just drills through it. It's effectively using a machine to do what used to be done by hand in terms of just digging through a wall. On the left here, we have what's called a cut and cover approach. So this top left picture is actually Melbourne Metro down in Victoria. This is one of the entries to a tunnel. We would call this a dive structure in infrastructure because it's where effectively the line goes down. In cut and cover, it's effectively exactly what it sounds. You dig out all the way down to where you would want the rail, you install everything, and you cover it back up. That's it at its core. Nowadays, obviously, it gets a bit more advanced in terms of retaining walls and slabs and such. We have much better track records with safety for it. But effectively, it's one of the useful methods. It tends to obviously be more used where it's a very shallow ground. So this dive structure that's being built for Melbourne Metro is only for the entry for the tunnel. The tunnel itself will actually be done using one of these, tunnel boring machine. Tunnel boring machines are quite interesting in that in some ways they've revolutionized tunnels and allowed us to create many more tunnels, longer tunnels and faster tunnels, and make them faster. But at the same time, when we talk about building a tunnel fast, the tunnel boring machine down in Melbourne gets 9 meters a day on average. That's a good day of tunneling. But tunnels can be kilometers long, so it takes a long time. Tunnel boring machines tend to be built for a specific project. Sometimes they get reused. I would love to see them reused a bit more, but they're very unique machines built for a specific project criteria, a specific type of ground. And fairly often at the end of the project, they're actually just tunneled into a hole and left there underground next to whatever you've built. But the advantage of them is that you have this one machine where it operates 24/7. It drills out the ground, conveyors out the dirt. They can bring in tunnel lining, and it supports around it. So 24/7 a day, this drill head is advancing, and people are lining the tunnel and such behind. So the tunnel gets built behind it as it goes. There's also a less common method called an immersed tube method. I thought this was interesting because this is actually how part of the Sydney Harbour Tunnel was built. Effectively, you build segments of the tunnel off-site, float them in, and sink them. Obviously, there's a lot of preparation work to be done and a lot of issues in terms of how you connect the tunnel segments, but it's quite an interesting method of construction. And understanding those methods is helpful because it helps us understand the cross sections, which play a role in fire safety and typical systems that can be provided and how they are provided. Here's a couple examples. This top right one and this one here as well are twin bore. So effectively you have two tunnels put through. They could be road-headed, TBM, or another method. And then you every now and then might have a cross passage in between. Or in some cases, you might even have a cross passages and a service tunnel, a third smaller tunnel in between. Oh, sorry. This top one here is what the tunnel might look like afterwards from a cut and cover, much more of a square box. This is where you might have traffic, and this top one is where you'd run all the services. This is what we call a trinocular arrangement. This effectively is just where two bored tunnels come into a station, and the station has been caverned out. And this one down here is quite interesting. It's a very large single bore. This is a highway in the US, where it's a double-decker of traffic. So one side road traffic goes one way, the other one goes the other way. On one side you have egress, this side you have ventilation, and there's also services. Typically, as fire engineers, you're not going to have much of a say in the method that gets built. Obviously, geology plays more of a role, as well as above ground and existing in-ground infrastructure. But understanding what's being built is a quick gut check in terms of what's available system-wise and what are likely outcomes. Now I'm just going to go through some of the key systems. I do have a lot of them to cover. I will say, sorry if I'm flying through this bit. Most of the slides here could probably be a presentation on their own, but I think it's important to understand a broad range of them. Before I do that, I want to touch back on the Australian standard for tunnel fire safety, AS 4825. It is a performance-based standard, and within it, it provides a trial concept design, things that you might be your starting point for a design on a tunnel, just as an indication. And what I think is really interesting about it is that it actually acknowledges that we use a risk-based approach. And you can tell that by how it categorizes different requirements based off what type of tunnel we have. Whether it's a short tunnel, a long tunnel, a high traffic, a low traffic, does it have intersections? Is it a metro passenger tunnel? Is it a regional rail? Is it a freight? These all have big implications on how we design tunnels for fire safety. They have implications on the number of people, the sizing of systems, design fires, the importance of operation, so forth. And similarly, what goes through a tunnel is really important. How you design a tunnel that is a road tunnel that does not allow any sort of trucks through will be very different than how you design a tunnel that's a road tunnel that allows heavy goods vehicles, trucks through, but not dangerous goods, or one that allows all of them through, including dangerous goods. Similarly, in rail, whether it's just passenger, whether it's more regional trains or freight as well, has quite an impact on how we think of and how we design systems. The first system we're going to talk about is tunnel ventilation systems. It's probably not going to be designed by you, but you're likely to be involved as a fire engineer. You'll have some input into it, but tunnel vent tends to actually be effectively its whole own discipline. My previous role at SFAIRP, tunnel ventilation was its own team outside of fire engineering and outside of mechanical engineering, just for tunnel vents. That's because while tunnel vent is used for fire, it's used for a lot of other things: environmental control, heat, dust, emissions, air quality. So day to day, the systems are used for more than just how we think of them in fire mode. And once again, the type of tunnel you have plays impact into sizing of these systems. If you have diesel trains, you're not going to need a lot more ventilation than electric. Now, tunnel vent systems, when we talk about them, we'll use them for smoke control, typically, as fire engineers. In a building, smoke control is pretty simple in that we want to send smoke up and people down. Typically, you take the smoke out as high as you can, and you bring the makeup air in as low as you can. Tunnels are obviously a lot more constrained in access for service system, access to people, and where people can actually go. This is a little figure from the Handbook of Tunnel Fire Safety, just to show how quickly smoke can spread and stratify. It's a 4 meter squared oil pan fire, half meter second of air velocity, and within 10 minutes, it's 800 meters downstream. So we have a lot of things to deal with here in terms of occupant evacuation and fire brigade intervention, in terms of managing this smoke spread. Tunnel ventilation systems are really big. Just need to get that out there in terms of when we're talking about infrastructure, flow rates are quite large. If you are working on a building and you have 100 meters cubed per second of smoke exhaust, somebody's probably going to ask you to double check that you're right and that you didn't add a zero somewhere. If you're working on tunnels and you have 100 meters cubed per second, somebody can say, is that only half of it? They're really quite large systems. I've worked on one where I think at a station we ended up with over 300 meters squared per second of air movement in fire mode. As an example, on the right here is an existing ventilation duct for a road, actually a bus transit system. It's about 4 or 5 meters by 4 or 5 meters, and there are 2 or 3 more of these just adjacent to it for this station. These 2 pictures here, if anybody's been down to Melbourne and you've seen that structure and wonder what it is, that is the Burnley Tunnel tunnel ventilation stack. That's a midpoint in the tunnel where it gets more smoke control and where some of the ventilation can come out. When we're talking about tunnel vent, obviously it's not one size fits all, and there are natural systems as well, but I'm going to talk about 3 most common systems. The first being what we call a transverse system. This is most like what you'd think of in a building. You have 2 ducts typically that run the entire length of a tunnel, and one provides air and one exhausts air. Ideally, one's at the top of the tunnel and one's at the bottom, but not necessarily always that way. It does require ductwork the entire length of a tunnel. Because of that, it also does tend to be more common in road than rail in terms of just the ability to actually implement it. And most modern systems or systems in longer modern tunnels are typically multiple zones. So rather than just have one long duct where it's always exhausting and one that's always supplying, they'll have dampers along them. So if, for instance, this vehicle was on fire, you could exhaust from here and you wouldn't supply in the zone, you'd supply from the adjacent zones. A semi-transverse system is much like the previous one, except for you only have one duct along the tunnel, and the air then, the other balance, say this fire exhaust, comes from the portals, the entrances to the tunnel. So you might be supplying air in at the top of the tunnel in non-fire mode, and it goes out the portal, and this fan would be reversible so that in fire mode, you'd effectively do the opposite. You would exhaust smoke out the top, and fresh air would come in the ends. A semi-transverse or a sort of mixed natural ventilation transverse longitudinal is something that I've seen a few times, particularly happens on existing infrastructure as well when you're expanding it or altering it. And then we have longitudinal exhaust, which we do call exhaust, but some engineers, first time to think of it, the first time they say it, won't really think of it as exhaust, because really it's pushing. Effectively, it's what it sounds like. Longitudinal is you try to push all the smoke one direction. So if we look here at this bottom figure in the bottom left, we have airflow coming in. Here's our fire. The goal is to get all the smoke to go downstream. This area here is called back layering, and this is effectively the fire pressure and thermal gradients pushing back against the airflow. When you're working on one of these systems, as a fire engineer might actually be trying to calculate and determine what is the critical velocity. That is the minimum velocity you need to ensure that there is no backlaying, or backlaying is very minimal. So all the smoke goes in one direction. And it's really important then to understand how big your tunnel is, and particularly gradients, as well as, I'll get to later, which way you want to blow the smoke. So in a road tunnel, particularly a road tunnel with one direction of traffic in that tunnel, the most common solution is that in a fire mode, you blow the smoke in the direction of traffic. Because the idea being that these vehicles ahead of the fire can continue to drive out, and then the vehicles behind should not be affected by smoke. These systems are quite commonly used in rail tunnels. It's what's being used on Melbourne Metro, Sydney Metro. All the rail tunnels tend to use longitudinal exhaust tunnel vents. It can be through shafts and supplies. In road tunnels, you'll also sometimes see jet fans on the ceiling, which I think I had a photo of here. These are jet fans. This effectively is doing exactly what the shaft would do as well. It pushes the air in one direction. And most of the time, all those sorts of fans in these systems are fully reversible, so that decisions can be made on which way to move the smoke. So for stations, I did say I wouldn't go deep into stations, but there was the first time I worked on a station, there was one really interesting aspect of it that I wanted to share. So for stations, typically at each end of a station, you'll have one of these shafts, one of these tunnel ventilation exhaust points, the TVS shafts, from the tunnel. You may in a station have all of or none of, or a combination of, over platform exhaust, exactly what it sounds like, over track exhaust, under platform exhaust. You may have platform screen doors, which help separate from the track. These are all systems which you could use to operate in fire mode. Stations, it's really not uncommon to have over 200 meters cubed per second, because typically what you would do is you would turn on the TVS at each end of the station to a complete exhaust, and then exhaust as much as you can down here. And to me, what's quite interesting here is, earlier I was saying how in a building we send smoke up and people down. Obviously, in an underground station, we're sending people up. And when you're doing modeling, one of the things you might be looking at is, can you get about 1 meter a second across the stair that goes down onto the platform? And that's effectively, you're trying to create enough flow of makeup air from upstairs and from outside that you can pin the smoke to the platform, so that once people are upstairs, they're safe. So it's sort of the reverse of buildings. You're keeping the smoke down and the people up. Egress. So tunnel egress, obviously, we definitely need to get people out of tunnels. Rule number one for tunnel is do not stop in the tunnel. If you're designing a rail system, if you're designing a bus transit, a road tunnel, the best thing you can do is design it, if you can somehow, in a way where never do you have a fire stop in the tunnel. Obviously, always there is a chance of having a fire in a tunnel that may result in a vehicle and personnel being trapped in a tunnel. So if you do start, you have to think about how you get people off the train or bus. Buses will have breakout doors or rear breakouts and emergency exits as well as the main. Trains typically adopt one of two methods or both. Sometimes they have end train detrainment, which you see here, this ramp. So you go to the end of the train, it folds out. And other times you can actually use the side doors and there'll be a narrow walkway in the tunnel that looks like that, except for it will never, ever be that clean, ever again. Tunnels are dark and dirty, and escaping from them is a slow process. Understanding this is really important in your design, in terms of how long does it take people to get off the trains? What are your options? Can walkways be used? Are they? Once we're off a train, we need to think about how we get people. Ooh, can you hear me? Yeah. How we get people to relative safety, or ideally absolute safety outside. Within tunnel systems, there are different approaches. So at the top left here, you see, or the center left, or center top, is a cross passage. It's actually part of the Melbourne Metro project going on now. Obviously, brand new, hasn't been finished. But this would be the sort of arrangement that you would have, is this connects two tunnels if we're looking at that twin bore arrangement. And the idea is if you get somebody out of the fire affected tunnel, or as we call it, the incident tunnel, and into the non-incident tunnel, the non-fire affected tunnel, they're in a place of relative safety. Other tunnels might have a divider between them. So if we're talking about a large bore, they might have a wall down them. Sometimes the only way out of a tunnel is back to a station or to a portal. Or to other exits. Understanding how people can get to those exits is really important, and being very well aware of that. Walking in a tunnel, even with the newest, nicest slab flooring, is not necessarily an easy task. It's not going to be as quick as somebody walking in a building. As you can see in the bottom right, there tend to be lots of trip hazards. It tends to be very congested, as you can see in the top right of an evacuation. And in terms of mobility impaired or evacuation impaired occupants, it's quite difficult to get them out. Generally, you have to rely on other passengers to assist them. Importantly, cross passages, often you'll hear the term refuge, area of refuge used for them. That term is typically used as it's a temporary spot where someone might wait a couple of minutes and take a breather. It's not meant to be they wait there and stay there until rescued by fire brigade. These cross passages are not nearly big enough to hold everybody from a train. I'm going to move now on to fire services. What sort of systems don't we include in tunnels? So if we talk about detection, sometimes you'll have onboard detection in your rolling stock. There'll be tunnel monitoring. Things like that day-to-day environmental control might include smoke detection in it, or looking for higher levels than expected of CO or CO2. With trains or buses, rather than public vehicles, you might have monitoring systems. So you can look for items that are in fault and failing. Generally, when we talk about public tunnels, as in anybody can drive in, versus a bus tunnel or rail tunnel where you get to control who's going in, different types of systems and different approaches because of how much control you do or don't have. On a project like Sydney Metro, there's effectively absolute control over what goes in the tunnel. Obviously, people can carry on goods to a train, but in terms of the actual vehicle that goes through and they have absolute control of that, which lets you make different design decisions. Services that we will talk about, sometimes they're automatic or semi or manual automatic activation detection. So for instance, I know of a tunnel where on detection, there's a timer that starts, and if nobody intervenes at the end of that timer, the suppression system activates, but the intent is actually that somebody is there and intervenes and makes that decision, not that it automatically goes. There's also tends to be onboard voice and PA systems and connection to something called an OCC, which is an operational control center. I think I have a photo of that in a bit. In road tunnels, in rail tunnels, you don't often have fire detection in the tunnel. You can have it, absolutely. It will depend on all sorts of decisions along the way and what type of traffic you're carrying, but it's less common than, say, in a road tunnel. Or in a road tunnel, it's much more common to have a linear heat detection. Linear heat detection, if you haven't dealt with it, is exactly what it sounds like. It's a wire that you would run along the tunnel, and when it gets too hot, it can activate and tell you roughly where the fire is, depending on what system you have. Some are more accurate than others, but it's a very long wire that would run along the tunnel. Both types of road and rail, it's not common to have CCTV, particularly in road. CCTV in a modern tunnel is there. In road tunnels particularly, I would say if you haven't in a while, next time you're in a road tunnel, be sure you're on FM or AM radio. If there's an incident, a lot of modern road tunnels have the ability to broadcast over top of your radio station within the tunnel and make an announcement through your radio to let you know what's happening. And with road tunnels, particularly, traffic control is very, very important when we're talking about members of the public driving through. What you see on the right is quite interesting. This was installed at the Sydney, I think the Sydney Harbour Tunnel, after like 3 or 4 trucks that were too tall kept hitting into the tunnel. This is a water curtain that has projected the stop sign on it that automatically activates if a vehicle too tall comes, but it can also be used in terms of there's an incident in the tunnel, don't enter. Rail. So in rail systems, I would say, again, fire suppression is a bit less common than in road systems, but it depends on what your rail system is and those decisions earlier. So a dangerous goods tunnel, that is also a vital piece of infrastructure. It's a lot more likely to have infrastructure suppression because you want it to be able to survive than, say, a metro system that you have absolute control on all the fuel loads and get to decide what vehicles go through there and the like. That said, there are a number of systems around the world that have it. I think Madrid Metro has installed them inside the vehicles like this. I think that's where that photo is from. And they can also be done in the tunnels. When they're not done, it's typically because the fuel loads are so tightly controlled and we've designed for large fires. When they are provided, particularly in tunnels, they're typically open head or deluge systems. So those are systems where all the sprinklers in one zone flow water at once based off control. So somebody has a control that opens a valve. When we talk about road tunnels, in Australia at least, the suppression is much more common. I would say most modern, almost every new road tunnel I know of in Australia is getting some suppression. These tend to be deluge systems, again, open head. They can be mist systems. There's some international research on that, but mainly deluge right now. Reminder when you're designing these systems is what goes in must come out. So if you're having any sort of wet suppression in a tunnel, they need to be able to design to get that out. So that then becomes a civil engineering issue in terms of drainage and sump pumps. And anytime we're working in life undergrounds, I always like to remind myself the most expensive thing you can add underground is volume, because any extra cubic meter you need is something that needs to be dug, braced, designed, lined, so forth. So it's really important to understand the impacts of that. And as I said, zoning decisions are important, and I think I have something else coming up on that as well. In terms of that management and traffic control, the operations control center for a tunnel, road or rail, you can think of it like an air traffic control tower or regional air traffic control center. They're monitoring where vehicles are, how traffic is flowing, where all the trains operating on time and in routes. Is there conflict or is there signal failure, so forth. 24/7 monitoring and really highly managed facilities. And again, this goes back to earlier I said the clients for these types of projects tend to be well-informed, experienced clients who have operated tunnels before. And brigade intervention, obviously a very important part and very difficult underground. When we talk about brigade intervention underground, particularly in tunnels, long tunnels, it's not uncommon for the distance between a cross passage in a tunnel between incident and non-incident tunnel to be more than 200 meters or more than 300 meters. That's a long way for someone in the fire brigade to have to go in the fire-affected tunnel to reach back to a fire. Radios and communications might not work efficiently. We do tend to provide hydrants in tunnels in Australia. Brigade will communicate with the Operation Control Center on controlling the tunnel vents, but it's really important that we work closely with fire brigade on tunnel design because of how constrained it is and how much of a risk it is, particularly air supply and access. So if you have to go on air earlier because the tunnel vent isn't blowing all the air in one direction, you might not have enough time to actually do anything by the time you get to the train from the nearest cross passage. Now I'm going to pivot over to structure. I know last week you had a great presentation on structure, so I'll be really brief about it. Fires underground tend to be hotter and faster based on fire tests, but also it obviously depends on what sort of vehicle and what rolling stock you have. But typically in Australia, design is done to the RABT curve, which is from German testing in a Eureka project. And typically that's part of the project requirements that would come to you as a fire engineer. Though ventilation decisions can actually impact your fire. So if you provide more ventilation, less ventilation, you could have a shorter, hotter, or longer fire. There's also a big issue with spalling, but again, I know you had a detailed presentation on that last week. Effectively, different design decisions are made in that, and it's not uncommon for every tunnel project to fire test its own concrete before that project rather than go off a standard. Similarly, structural fire resistance in tunnels can be provided different ways. Sometimes there are additional linings, like you see up here. Sometimes it's shotcrete, which is sprayed on concrete. Polypropylene fibers are often put into tunnel linings to help reduce spalling. So last week, the presentation covered a lot about spalling in terms of as concrete heats up, particularly when it heats up very fast, like it would in these very well insulated environments, the water vapor in it expands and can effectively blow out chunks of concrete. Polypropylene fibers in it melt first and create little air pathways for that steam to escape. Zoning. So I've mentioned zoning a couple of times now in terms of those systems. In buildings, zonings is really important in terms of, understanding how does smoke detection, EWIS, and sprinkler zones match up. In tunnels is also really, really important so that all the controls and the appropriate items are activated at the right time in a fire event. For instance, that longitudinal exhaust, knowing which way to activate it is really important. And that will be based off what you know about where the fire is along the train, what car, what zone the vehicle is in, and the nearest exit. So I would say anytime you're working in a tunnel, it's really important. Effectively, you could map out, as this manufacturer has done, a little example of what are all your different systems that have different zones, and how do they overlap for different fire scenarios, and are there any conflicts or issues with that? So I just went through all the systems individually. If we try to bring it all together, there are lots of questions that need to be answered when we're thinking about these together. So I've already mentioned which way do you ventilate if you're using longitudinal is really important. That can be based off where a fire is in a vehicle, but also where the exits are. and how easy it will be for people to reach exit. There's also the question of when to activate systems, particularly ventilation. There's some different mindsets. The projects I've worked on have mostly been activated as soon as you can, but there are some other mindsets of don't activate it until after evacuation, because you might want to let the smoke layer stratify as much as possible so that people can escape underneath. That has a big role. Similarly with wet systems, so fire suppression. One of the big reasons you don't see them on platforms in Australia is there are big concerns of, if that system activated, would the cooling break the stratification of the smoke layers and actually make visibility, egress, and access to the brigade much, much worse. So those are sort of conflicts that need to be considered. And which systems do work with each other or compete with each other. How many trains do you have between ventilation points or cross passages is really important in the tunnel. If you have more than one, can 2 trains be stuck and have to evacuate, or just one? Can one of them reverse? Where are the cross passages related in relation to where your ventilation points are? Will occupant flows merge? So if you are doing end train detrainment and you have people evacuating out of each end of the train and they go through cross passages, are they both going the same direction to a station, different directions? Are they going to interfere with each other? How do brigade access that area while occupants are evacuating? For these tunnel fires, we're not evacuating 5 minutes, 30 minutes, 40 minutes, and accessing for fire brigade as well is quite delayed in terms of getting access to it, to the fire. And then obviously before you actually let anybody into the non-incident tunnel, you need to make sure that no trains are running or that road traffic is stopped in that tunnel. Otherwise, you're introducing new hazards. So just quick example, I know time's out, I'll try to speed it up a bit. Quick example of a longitudinal rail system. So direction of travel, if we have 2 vehicles, and these is the ventilation zone. So in this case, we have 2 vehicles in the ventilation zone. A decision needs to be made then on which way to ventilate and how this train evacuates and the like, and that needs to be communicated quickly enough to control how people are moving and to then inform how fire service can intervene. Just a quick look at the Eurotunnel, because I think it's a really interesting tunnel in terms of design and that criticality of service to Europe. In blue here is the actual rail tunnels, and in red is the service tunnels. You note there are crossovers where they overlap along the channel. That's actually been done so that if there's damage or the like, they can still operate it and operate it in both directions and just slightly reduce traffic. The original design of the Eurotunnel didn't have any fixed fire suppression. After a fire, they actually installed fire suppression in 4 specific points, with the idea of some analysis that a train, even disabled by fire, should have enough momentum to make it to one of those points to make fighting the fire easier. It's quite an interesting system, and it's a good showcase in how to design critical systems with some redundancy so that the entire environment could continue to operate. I won't go into too much detail given time, but I talked about tunnels, talked very briefly about stations. When we talk about tunnels, stations, and integrated over stations development, things get even more complicated. These are some cross sections from Metro Modern Place from the major planning portals on New South Wales website. When we talk about overstation developments and tunnels and stations, we have to think about how smoke moves, how people move, how different things are zoned, and how fires in different areas could impact the operations of other areas. So, for instance, you would never want to design a station in a way where a fire in the building would stop the train station from operating. And this all gets more complicated as we look at how services and people and operations move and are connected. In some cases, you can separate them nicely, and in most cases, you can't. Earlier, as I said, on rail projects, particularly safety assurance is not just an outcome, it's a process. It has to be recorded. Any inherent risks aren't hidden. They're actually written about in plain sight, transparently. It's not unusual to end a project with a lot of risks still open and existing. It's just that they've been identified, understood, mitigated so far as is reasonably practical, and then accepted. And in that, there are a lot of hands on our infrastructure project. These are all different roles a fire engineer could play on a project, and it wouldn't be uncommon for all of these to be different people. So lots of fire engineers might get involved in one design, and that broad, diverse thinking is actually really important. And yes, sometimes fire engineers can butt heads about how to approach it, but really it generally ends up creating those better outcomes because that process is followed in terms of transparency of hazards and risk and mitigations and the approach and mindsets. And then this is just a partial list of references. If you are just handed a piece to work on your first ever tunnel project, I highly recommend the Handbook of Tunnel Fire Safety. Yes, it's a bit older, but it's really great resource, and it's not too dense. It has a great list of historical fires and lessons learned as well. There also are a surprisingly large amount of information available just online on those infrastructure projects. And particularly in New South Wales, it's really great about major projects being published online, not the final designs, but at least inputs and initial concepts on the major projects portal, which has great information about rail projects, road tunnels, but also other major projects. And that's it. Sorry, I kind of flew through that.
Nate, thank you for this presentation. Really wholesome on a lot of aspects of the fire safety strategy for tunnels. A lot of things to learn from it and to take from it. So yeah, I'd like to thank you. I invite, sorry.
I guess questions, I'll answer this first one.
Yeah.
So reliance on other passengers assist with egress. Do I think that's SFAIRP, or do I think other measures should always be introduced? I'm hesitant to use the word always, just because each project is different. I think SFAIRP would require us to, well, at least always consider other measures, whether they're always introduced or not, depends on design. I would say in new projects, we do need to do better and are doing better. So more recent projects, rather than having all those metal grates at the bottom, they tend to be slab tracks, and they try to design them such that you could fit a wheelchair through them. But it is about that balance between reasonable practicality and giving better safety outcomes. Fuel loads. What are my thoughts on fuel loads, especially those from airports? You must be talking about the new metro line at WSA. Fuel loads, I mean, are variable. They are things we think about. They, on tunnel projects and on that rolling stock, so I didn't talk much about rolling stock, is fuel loads really come into more of that rolling stock for rail when we're talking about that. Rail vehicles undergo a significant amount of testing in terms of what fire loads would come out of them, but then also they're monitored live 24/7. So like Sydney Metro up at Chatswood, you'll notice cameras that are looking for, can people hide material somewhere? And risk registers for projects will include the idea that someone traveling from the airport will have different baggage than someone commuting to work and has a bigger fuel load. That definitely is something that should be considered. Steve Parrish, how is changing characteristics of population? Steve, that's a great question. I think hopefully it makes us think more about that earlier question of assisting other passengers and egress and access. Is transport for a long time has served as a great socio-economic equalizer among the poor and the wealthy in terms of traveling to and from cities. And I think in the future, more now, we're going to realize that it also has to be physically equitable in terms of that access. For fire, that will mean much higher proportions of slowing walking, of people needing assistance and the like. Post-incident variant.
Nate.
Yep.
Sorry to interrupt you. Could I ask you to read the questions? It's just because I
sorry.
sent directly to you, so I cannot access them. So just for the record of the video, so people know what you are talking about when you are answering. If that's
sorry. The first two.
That's okay.
Sorry, the first two questions were direct messages. They were that I mentioned reliance on other passengers to assist egress. Do I think that's SFAIRP, sufficient in addressing it SFAIRP, or should other further measures always be introduced? The second direct message was, what are your thoughts on fuel loads, especially those that are traveling to from airports? The third one looks like it was to everybody. It was, how is the changing characteristics of the population aging affecting fire engineering and infrastructure? And this next one is post-incident fire brigade are responsible for potential search and rescue in the tunnel. Should further consideration be given to increasing structural fire resistance of tunnels for this reason? My simple answer to you is, in terms of tunnel, I can't think of a tunnel where I would design it as structural failure in any sort of fire is, or in a typical fire is acceptable. Because they are so critical, we typically design tunnels to survive the fires we're looking at. We look at them to survive burnouts, particularly because we also need to think about post-incident repair and replacement. Peter Johnson gave a great example of this, I think, a couple of weeks ago to SFP, of two similar tunnel fires, one in Victoria, one in the US. Where in Victoria, there's suppression, and the tunnel was closed for a couple of days. And in the US, there wasn't, and it was closed for 6 months. So I think definitely we need to be looking at how fire brigade can safely intervene in tunnel and respond in terms of structural resistance. But I also think that some of that should be covered in achieving the goals for operational continuity and repairability. Any other questions?
Well, I had one, but just out of plain curiosity, when you were talking about the mechanisms to keep the smoke inside a train station that is underground, so you pin it, inserting air from the surface, right?
Yes.
So I was just wondering what other kind of safeguards you have to put in place so that smoke doesn't migrate to places where you don't want it to go.
So it's not uncommon for these to also have smoke baffles. And I think Jared Alston, who's designed a lot of tunnel systems, used the word architectural commitment. Is a good word to design to think of when you think of how stations should be designed. Is that there will be a lot of architectural design that is designed particularly to assist in that fire mode, to keep a deeper smoke layer down by the platform and prevent it from coming up. There's also significant restrictions on any sort of actual material down there that can burn. If you have a fire at platform level in a train station, it's either going to be the train or something somebody brought in.
Yeah.
There's not much else there.
Yeah. All right. Thank you. I think in the meantime, we received 2 extra questions in the chat.
Yes, I think I've gotten all wind effects typically taken into consideration in the design of smoke exhaust systems. Yeah, I would definitely say they are, or they can be and they are, but it also depends on what sort of system and where. So along a long running tunnel, we're looking at the longitudinal and it's not really that relevant. If you look at more of an interchange or with like a shallow bus station, wind effects are much more prevalent and much more involved and should be considered. And then also, while you ask for tunnels, I will bring up in buildings where exhaust points are put really needs assessment in terms of wind can overcome smoke exhaust systems themselves, in terms of preventing them from operating, not just adversely providing makeup air. Yeah, And then I think that was the last question I have.
Yeah, I think there was one regarding to, if you could share any experience on the design for battery EMU running on Metro.
I didn't work on the battery portion of Metro Channel, but I can talk about a bit about lithium-ion batteries really briefly, because that's easily a seminar on its own. Key thing, the key advice I had to any fire engineer working on anything with batteries is to understand that thermal runaway and fire are not necessarily the same thing. You can have a thermal runaway that creates a battery that gives off combustible gases and create an explosive environment, particularly in an enclosed tunnel. Or you can have a fire where it also causes thermal runaway, but in theory, a lot of those combustible gases are being consumed as well. So batteries do need to be thought of and designed, and your ventilation system would play a part in terms of that. If you have a vehicle with a battery that's disabled and the battery's in that thermal runaway mode.
All right, thank you for your answer. And another question came to my mind in terms of priorities when you are designing the whole fire safety strategy. Is there any kind of priority? So in terms of the structural integral, the structural integrity of the tunnel, or it's more about the safety of the occupants, or it's just a balance of all of those elements that has to be taken into account?
So I would say, I mean, it is called fire life safety because life safety comes first. And under that rail legislation, the SFAIRP philosophy applies to safety. But I would say if you follow that SFAIRP process and that mindset of identify any risk and hazard, and just be sure it gets tracked into the right person who's there to address it and there to review it, that you will cover everything. And when I say that, I can bring up an example of if you as a fire engineer are sitting in a meeting and you identify a hazard, I don't know, a unique trip hazard. Yes, you're not meant to solve that, but the process would require that you record that and have it transferred to the person who is looking at that. And I think through that sort of process, you'll capture all of the structural issues, the stability, the repairability, the operational, and the life safety.
All right, thank you for your answer. Nate, I would like to thank you a lot for joining us today, for your presentation, your answers to all the questions of our attendees. Yeah, if you like to, I think someone is raising their hand.
Sorry, Julian, it was me.
Oh yeah, hi Cyrus.
Hello, hi Nate.
Hey, Staff.
Two questions. One is, when are you coming to Brisbane? You can answer later. The second one is, I'm really sorry I missed the first 50 minutes. I had some technical issues. But I will, in case you answer that question, apologize. Through your presentation. I know that you're also pretty involved with the BCA and everything. Most of us know that underground stations, the Building Code of Australia doesn't really classify them as a building or as a structure. Are you aware of any changes that are going to come up to include underground structures or tunnel structures? You know how they recently made a change and they included mass timber, calling it massive timber. Have you heard of anything about tunnels?
So I have not heard anything about tunnels in terms of building code and that under development. I have seen like the BCA still does get applied to stations. It just
for above
often even the underground portion, it's just often you just get silly answers like our underground station is a large isolated building because the entire tunnel is part of the fire department.
Oh, I see. Okay.
So you get silly answers. As far as I know, it's not in development, and I would think that I'd like to think ABCB would be of the view that there are other areas of building code that are much more in need of attention and that effort They're looking at quantifying fire safety, and that's
Wow.
where their mindset is. And for tunnels, frankly, I don't think we do enough of them in Australia. Like, yes, we're doing a bunch now to justify developing a whole new code of our own for them.
Oh, I see. Okay. Thank you. That was
No
interesting.
worries.
Thanks, mate.
All right. Oh, I have one more question, looks like. In vehicle fire, moving me. In a vehicle fire, the fire will likely be moving, making detection of the fire location difficult as variable. If we're talking, I assume we're talking about road there, not rail, because the rail is a lot easier to answer that. Road, I would say a lot more of it is that CCTV, but it's also designing for error. So for instance, the last road tunnel we worked on, the deluge system, we made sure we had enough water to operate, I think, 4 zones, but expected that no vehicle would be across more than 2 zones. So if inadvertently the wrong zone was activated, we could still activate another zone without having to wait for additional water to refill or having to go manually reset anything. To CAS 4825 differentiating between rail and metro tunnels in the future. In the trial concept design, it already does, Steve. But if you mean in more detail, I'm not really sure. I haven't been involved on that committee. I do know there are a couple of people on that committee doing changes, but I'm not sure what the changes coming up are. Hopefully, it will include a bit more on metro type vehicles and autonomous rail vehicles is my hope, much like Sydney Metro's approach.
I think that's it for now. So thank you, Nate, again for your great presentation. We will make this talk available in our YouTube channel, as we do with all the webinars we have hosted in the last month. So yeah, Nate, thank you very much. We hope we can have you for a future event, probably in person and on campus. For now,
That'd be great.
thank you very much. I would like to share something with the attendees pretty quickly. So just a second. So we'll be hosting another webinar the next Thursday. I know these are usually on Fridays, but yeah, it's going to be presenting David Barber, a principal with ARP, where he will be talking about research for engineering solutions in high-rise mass timber buildings. So please, if you are interested, feel free to join us in this seminar. And as I was mentioning before, we will make the video available. We have videos on some other topics, also with fire safety in tunnels, infrastructure, traveling fires, wildfires, more fundamentals, some of the experience of our alumni. So if you are interested, please don't hesitate to join us. Thank you again to Nate for that great presentation, and to our attendees for joining today. Have a great weekend. Goodbye.
Thank you.
Thank you.
Thank you.